Okay, so we now have a way of generating fields from irreducible polynomials, and we know how to check polynomials are reducible. So now let's start talking about field extensions. So we need section 1.3. This is called field extensions. And as usual, we start with definition. Definition 1.3.1. Let K be a field containing another field. Field F. Then we call K a field extension of F, and F a subfield of K. We denote this by K over F. So this is K is a field lying over F, and its degree by this, and its degree, which I'll denote by K 2 dots F, is a dimension K as an F as an F vector space. So K lives over F. They're both fields, so you can think of K as a vector space over F, and then the degree is just a dimension of this vector space. We say field extension is finite if this degree is less than infinity, so it's a finite number. Otherwise, we say it's like an infinite degree extension. Okay, so let's look at what the degrees of the fields we get by adjoining some irreducible polynomial are. So here's a proposition 1.3.2. So let F be a field, and P of X in F of X, and irreducible polynomial of degree n. Then if I set K to be this field, F of X, quotient out by this ideal generated by this polynomial, we saw that this was a field before. Then this is a field extension of F, and the degree K over F is exactly n. So what I get by quotienting out by some polynomial, irreducible polynomial, is a new field, and this new field has degree, which is the degree of the irreducible polynomial that I used to construct it. So this thing here. So let's prove this. So proof. So well, I think we're gonna find a. We know that this is a field, so all we need to check is that. Well, this is clearly F lives inside of here. So all we need to check really is the degree of this extension. So I claim that I know what a basis for this is. I claim that the image of 1 x to the n, x to the n minus 1 in K. So you think of these are polynomials, and these are polynomials in F of X. You think of what their image is inside of this thing here. I claim that this K is a basis for K over F. So we gotta check that it spans, that it's linearly independent. So first thing to note is note that if F of X in F of X has degree less than n, can be written in terms of this basis. That's clear because f of x, I'm going to say I take a polynomial of degree less than or equal to n, then it's, or strictly less than n, then it looks like, some constant plus a1 times x plus a2 times x squared, so on. So clearly that can be written in terms of this basis. But what happens if you take a polynomial that has degree at least n or greater? So now, it can be written in terms of this basis. So now assume the degree of f is greater than or equal to n. Then this is where this Euclidean domain and having a Euclidean algorithm comes and helps us. So assume that we have this thing, then by polynomial long division, we have that we can write f of x, we can write it as some q of x times p of x, the polynomial that I'm using to quotient out my ring y. This, I can, by doing long division, I can write f of x like this, by definition of this being a Euclidean algorithm, with a degree of r strictly less than n, which is the degree of f. So f of x is congruent to r of x modulo p of x, right? If I think of what this polynomial looks like in K, I can this q of x times p of x. This is in the ideal generated by p of x. So f of x, once you forget what's in this ideal, you can think of it. It just looks like r of x. So in K, f of x just looks like whatever r of x is. So not p of x. I write this like modulo this ideal. So again, we can write it in the 1x x to the n minus 1 basis, right? Because I can replace f of x with r of x. R of x has degree certainly less than n. So now my basis works. Well, this is what I claim my basis is. I'll put it in these polynomials. So I have it that my claimed basis, at least it spans it. So now we gotta check that it's linearly independent. Say remains to check that 1x x to the n minus 1 is linearly independent. So let x bar I denote let me not go too much into this notation. I already said that these xi's were the images of x inside of here, so I don't need to put some bars. So assume, for contradiction, that they are not independent. So we can find, what do I call these? A0, am minus 1 in f, not all 0, such that a0 plus a1 times x plus an minus 1 times x to the n minus 1 equals 0. I have my basis. I'm assuming that they're linearly dependent, so I can find some non-zero AIs such that this thing holds. This means I should write this as mod p of x because I'm working in K. So this means that p of x divides a0 plus an minus 1 x to the n minus 1, now viewed as some polynomial in z of x, viewed as some polynomial in f of x. Right, I have this polynomial, it's congruent to 0 mod p of x, so the same congruent, you know, as you were used to for numbers. When I write mod, the same properties somehow hold. So something being 0 mod some ideal means this, some principal ideal means that the element that in this principal ideal that generates it divides your thing. Just like if I said, you know, n is congruent to 0 mod p, it means that p divides n. The same thing works in this polynomial. So this means that p of x divides this polynomial, but this has degree n minus 1, which is less than the degree of p of x, which is n, which is impossible. So this is impossible. Okay, so if we had some sort of linear dependence relation, then this would give me a polynomial of degree n minus 1, so a smaller degree, which p of x divides, but p of x has degree n. So it's like you're trying to divide a polynomial of degree 9 by a polynomial of degree 10, so it doesn't work. So it's impossible. Therefore, 1x to the n minus 1 must be linearly independent. And we check that it spans, and we check that we have linearly independent basis vectors. Okay, so let me give definition of some other types of fields. So here's definition 1.3.3. If I let K over F be a field extension, and I take some elements in K, and I'll take some alpha 1, alpha n in K. I'm going to let F alpha 1 to alpha n be the smallest subfield of K, which contains F and all of these elements, alpha 1 to alpha n. So you can call this, sometimes it's called like we'll also call this the field generated by alpha 1 to alpha n. Known as the field generated by alpha 1 and over F. If we're in a special case where we just take one of them, then we give this a special name. We call it a simple element, a simple field extension. So a field generated by a single element is called a simple extension. So I've just, instead of having n things, I only have one thing. I.e., f of alpha is a simple extension of f. We call alpha and k, the generator in this case, the simple, the primitive element of the extension. So I take a single element, say alpha, and I make this field f alpha. This is called a simple extension of f, and the element alpha that I've taken is called the primitive element. It's the one that I'm using to generate my new field. Now here is the one of the more important results that we have. We're linking these sorts of fields where I've joined a bunch of elements with these fields where we divide by some some polynomial. So it goes as follows. So here, this is important enough that I decided to call it a theorem. So I think this is our first theorem. This is theorem 1.3.4. And it says the following. So let F be a field and P of X an irreducible polynomial in F of X. And moreover, let K over F be a field extension containing a root alpha of P of X. So I look at one of the roots of my irreducible polynomial. I find a field that contains this this root. Then there is an isomorphism as follows: F of X mod P of X is isomorphic to this field F alpha. And this map is given by sending say F of X to F of alpha, i.e. evaluate at alpha. You might wonder why I've chosen my field here. So I need to assume that there exists a field somewhere which contains my root. You can think of it, if there are some philosophical reasons why this is important. If you don't want to worry too much about this, and you can ignore this thing if you just assume that that you have the complex numbers. And the complex numbers contains the roots of any polynomial by the first fundamental theorem of algebra. So you can always take K to be the complex numbers, and then there is your field, which can, for any field that you've taken, as long as it's an extension of Q or something, then this works. So you could take the complex numbers if we were throughout our course. But at the moment, I have abstract fields, so it's not clear that they live inside the complex numbers or not. But all I want to assume that there exists somewhere where some field which contains a root. But you see that the statement doesn't actually have this. Okay. So I'm claiming that there's an isomorphism, and I'm claiming that I can tell you what, and I told you what it is. So let's check this. So proof. So I'm going to let phi denote the map. Yeah, F of X goes to F of alpha. So, let me just be a bit more precise. The map from F of X to F of alpha given by a little polynomial gets sent to the evaluation at alpha. So this is a map starting from the top of my quotient, so from my polynomial ring. So I've given this a name. First thing to note is that P of X is in the kernel of this map. Why is that the case? Well, if I take P of X and I evaluate at alpha, I get 0 because by construction, alpha is a root of P of X. So P of alpha is 0. So under this map, P of X goes to 0. So that means that it's in the kernel. So we get an induced map so maybe I should call this phi primed, called my induced map phi, which goes from F of X mod P of X, because it sends the thing I'm quoting out by to 0. It's in the kernel. This means that this defines me. Okay, I'm not saying that's morphism yet. This defines me a map like this. Yeah, so the fact that P of X is in the kernel means that this ideal, this is in the kernel. Remember, the kernel is an ideal. So you can sometimes say that this means that the map factors through this ideal generated by P of X. And you can check if you want, but this means that I have a well-defined map now from the quotient to f of x. So we want to show phi is an isomorphism. So we need to check that it's both injective and surjective. So what's the first thing to note? Note that phi of x plus anything in this ideal equals alpha, and if A is an F, then phi of the element A is just A. So the image of F has, sorry, the image of phi contains F and alpha, because I can hit them both. Here's how I hit every element of F, and here's how I hit the element alpha. Moreover, phi is a field homomorphism. You can check this. So its image again is again a field. So I stated before that if I had a ring homomorphism, the image was a subring. This extends to fields. If you have a field homomorphism, the image is a subfield. In any case, the image has to be a field, and I just checked that it contains alpha and A of F. And now recall that F of alpha was defined as the smallest field which contains both F and alpha. So F of alpha has to be contained inside the image. Therefore, by minimality, I guess, of F of alpha, we have that F of that phi is surjective. So the image has to contain F of alpha, but the image also has to be inside of F of alpha because it's a map to F of alpha. So we'll need to check his injectivity. So it remains to check injectivity. How are we going to do this? So this is actually pretty easy. Recall that, I can't remember if it's lecture 1 or 2, that the kernel of any non-zero ring homomorphism is a prime ideal. Maybe in I forgot that. Maybe I misstated it in the thing. I'll have to check. It's a prime ideal, and the only prime ideal in a field is the zero ideal. Maybe I didn't state this before, but it's true that the kernel of any non-zero ring homomorphism is not just an ideal. It turns out it actually is a prime ideal. So this is the kernel, and I have this is a map between fields. So the only prime ideal in the field is the zero ideal, and so the kernel has to be the zero ideal, which means that the kernel is zero. So the map is injective. So kernel of phi has to equal the zero ideal, i.e. phi is injective. And we're done. This finishes the proof. So now we have a link between our fields taken by quotienting out by some irreducible polynomial and some fields given by adjoining an element. So I'm going to just show you, these are maybe the fields that you're more used to seeing, these are where we adjoin an element. So here's an example why this is useful. This result tells us, as we saw before, that q join root 2 is isomorphic to q of x join x squared minus 2, this ideal, which is nice, but notice that for my definition of the isomorphism, I said in my theorem, let me just go back up, I picked the root of my polynomial and then I used this as my to define my isomorphism, right? I said I pick a root of my polynomial and I say evaluate your polynomials at this root, but I didn't tell you which root to choose. You could choose a different root. So notice that we also have, if I had taken the other root in this case, q of minus root 2 is isomorphic to q of x over x squared minus 2, because I can just take the map and evaluate it, the polynomial and evaluate it at minus root 2. So if you combine these things, you have q of root 2 is isomorphic to q of minus root 2. So you have this sort of isomorphism, but these isomorphism, this field q of root minus 2, q of root 2, whilst they're isomorphic, they're not canonically isomorphic. There's some sort of choice in between. You have to move your roots from one side to the other. So both of these fields, q root 2 and q root minus 2, are maybe not quite well defined. If you notice, technically I assumed that there existed some k which contained the root. In this case, for example, I say, well, I'll take my k to be the complex numbers. The complex numbers contain the root 2. So there is a field which contains the square root of 2, or a root of this polynomial. So I can do this, but this q of x mod x squared minus 2 is the more intrinsic algebraic object. It's defined without me having to mention that the complex numbers exist. So, and again, this is just some philosophical reasons. If you look at the type notes, you'll see a more detailed discussion as why this is somehow important. But let's not worry too much about this now. So I'll finish here for field extensions, and the next time we'll talk more about start talking about algebraic extension.